So Archana did a really great job motivating gravitational wave astronomy in her talk, but just a quick recap so that we can better understand our sources of noise and why they're bothersome. So our space-time strain, h of t, it's proportional to the second derivative of the quadrupole moment of the system in question. And this makes gravitational waves that propagate as waves at the speed of light, and they induce this space-time strain, so this change in length over length. And there are two different polarizations of gravitational waves. One is called cross, and the other is called plus. And it's this polarization that motivates sampling more than 1 degree of freedom in space, and then this motivates the shape of our detectors. So the LIGO detectors have this L-like shape. So we have some input laser light that enters the interferometer. It's split at a beam splitter. 50% of it goes down what we call a Y-arm, and 50% goes down an X-arm, circulates in these arm cavities. And then when it recombines at the beam splitter, if either of these arm lengths have changed relative to the other, this will induce an interference pattern at our output port. So we're just counting photons, the number of photons over time, and this is our gravitational wave signal. But it's not really that simple. So this is on the scale of an increasing reality. So this is the simplest picture that I could give. And then the actual reality is that there are dozens of photodiodes and optics. All of them are controlled, sometimes by multiple independent control systems. And this is all, of course, installed by hand. So we're also thinking about vacuum contamination in the environment, and there are many different places for noise to couple into our gravitational wave signal. So we have two of these extremely complex instruments. So one is, they're both in the United States. One is in the desert in Washington, and the other in the swamp in Louisiana. And it's also important to understand more about our analysis to see what's important about how the noise is affecting our ability to make astrophysical detections and statements. So this is the matched filtered analysis. So essentially our detection statistic rho is just the signal to noise ratio of our data with the match template. So that's just the inner product between the data and the template that you're matching it with. And this is just broken up into cosine and sine components. And then you normalize this by your noise curve, and we'll see an example of that on the next slide. But that's our detection statistic, so this is signal to noise ratio, and this is the results of the search for binary black hole coalescences from LIGO's first observing run. So what you can see here in red, this is the search results itself. So that means that we took our data, and we took our analysis that is described by this detection statistic, and this is the output. And we show this relative to a background. So the way the background is done is you take the same analysis and the same data from the two detectors, and you slide the detector data relative to the other detector by more than the travel time of the gravitational wave. So this way, we don't need to model what our noise looks like. We're using our real noise, which should produce some comparable rate of false triggers from transient noise sources. But since the detector data is shifted, we know that these cannot be real gravitational waves. So we do this many, many times, which is why you can see the rate goes far below 1. And what you're looking at here, so in black, this is the search background, including all of the data that was included in our first observing run. But what you can do is, so once you've confirmed that the signal is a real signal and that we're confident in it, and the way that we measure that is by looking at this significance scale up here, which is just the standard deviation if you plot this to some Gaussian curve. So once we've decided that we're confident in the signal, we can remove that piece of the data from our analysis and recalculate the background. And this way, when you're shifting the data of one detector with a real signal in it relative to the other detector, you don't get noise beating off of the true signal. So in order to determine the significance of the next loudest event, that's just the same plot here, but now rescaled, so that this plot in blue is now, or this trace in blue is now this trace in black. So this is how we can determine the significance of the next loudest candidate event, which was what we call the Boxing Day event in December. So this is essentially how the analysis functions. And to get a better intuition for signal-to-noise ratio, so in order to improve the significance of any particular candidate event, we want to do one of two things. The first is decrease our background events, so the significance of our background, and that means instrumentation, that means thinking about what the noise is doing and how we can make our analysis either more robust to it or remove it from our data. And the other thing we can do is improve the signal-to-noise ratio of any particular event that we see in our data. And we can do that by trying to push down these noise curves. So the signal-to-noise ratio is essentially, you take so this is amplitude versus frequency, and then these are each of the three candidate events from the first observing run. And their amplitude versus frequency is plotted here, and their signal-to-noise ratio is essentially the integral between this amplitude and the noise curve below. So something else that we're thinking about is how to improve our noise over time, and not just worried about noise transients that might mimic gravitational waves. So as has been mentioned, LIGO data is non-stationary, including at times, over times, relatively short time scales that we use to estimate our power spectral density to do these analyses. So this is an example that Gayatri and I were actually just looking at. So this is from the first observing run in the LIGO-Livingston detector, but we also do see it in the second run. So this is time in seconds, and then frequency. So what you can see is over about the scale of 2 minutes or so, you have these sort of vaguely harmonic wandering lines that appear and then disappear. And this tends to produce false triggers for some of our longer duration templates, which is even more problematic. It's more of the template parameter space that we're polluting rather than just the very, very short transient glitches that we see. So Sukanta also mentioned that we have different glitch classes, and these are some whimsical examples of some things we see. These are all real-time frequency spectrograms of LIGO data from the first observing run. So fun fact that this column on the left here, those are actually the real names that the experts use to refer to these glitches. Not as much on the right, although Fringy the Sea Monster is probably my favorite. But by the metric of what kinds of glitches are impacting the search backgrounds, what are contributing to that histogram, the tail of high significance noise events, there are less than 20 classes per detector. So we have noise, we recognize that we have noise that's influencing our ability to do gravitational wave astrophysics. So what can we do? We try to diagnose it and mitigate it as much as possible. And a very important part of that is auxiliary channels. So these are other collected time series that measure things other than our gravitational wave signal. So there are about 200,000 of these channels at both sites. So it's a big data problem to analyze all of them statistically. And this just gives you a sense of some of the comparisons we might do. So this is an example gravitational wave strain channel that has 4 transients in it, and 3 of them match up, 2 with this microphone channel, and then another with an anemometer measuring wind. So both of the detectors are equipped with a full suite of physical environment channels. These channels measure not only wind speed, temperature, but also some things that might influence fast changes in the interferometer. So these are vibration sensors, accelerometers, microphones, magnetometers, and voltage monitors that are monitoring the power that's going into all of the equipment that's driving the control signals for our interferometers. And the SAMC Working Group 3 should expect, due to a very recent memorandum of understanding with the LIGO scientific collaboration, to have access to some of these channels, to the full suite of these channels from the prior science runs, S6. So that'll be, I hope, very useful for us to practice with. So to give you a sense of how this goes at times, so this is a story that I like to tell that took place last summer. So this is the summer, I guess, oh wow. So this is summer 2015, so a little less than 2 years ago. So at LIGO Hanford, we noticed that there was a semi-periodic glitch that happened exactly at 60 hertz, and it occurred about once an hour, and we always saw it with the magnetometers, coincident with the magnetometers at the end of the Y-arm. And we noticed that as time went on, that as the weather got cooler, the time between each one of these glitches kept getting longer. So we were thinking, okay, maybe it's temperature related. So eventually, two of these fellows, so this is Vinny Roma and Borja, went down to the end station with a handheld magnetometer, and at the time that we predicted one of these glitches would happen, and isolated the source to a refrigerator that was holding cool water for people to come out of the vacuum chamber dressed in their bunny suits with, that never got unplugged. So the solution to this, no refrigerators were harmed in the making of our last science run, but we did unplug it, and that solved that problem. So that's the ideal case, is that we remove the noise from the data. If we can't do that, then the noisy data is vetoed using this auxiliary channel data. So I will say, okay, anytime that I see this particular magnetometer that has a glitch that looks at this frequency, then I'm going to cut that chunk out of the data. And this is what we feed to the astrophysical analyses while they're searching for gravitational waves.
What was this coupled with?
That is an excellent question. So there are many different opportunities. So all of the instrumentation that feeds the control systems that control the position, including length sensing, which is directly proportional to our HFT signal, go through these electronic racks. So if I would suspect that first, but I do not know that for certain. So this is another one. This is an example from the second observing run. So this was sometime in, I think, early December. So this is, was before we vetoed it. This was in real science time. So this is in observing mode in data that we would otherwise be searching for gravitational waves in. So this is our HFT channel. So this is a spectrogram at 16 seconds worth of time versus frequency that goes up to about 2 kilohertz. And then this is the same normalized spectrogram. So we're looking at the normalized energy of the signal for a microphone. And this is PSL, just means pre-stabilized laser. So this is the laser source, a microphone in that little room where we keep the laser. So we're looking at this and we're thinking, what the heck is this? So you see it's broadband, it's above 500 hertz, it's got all this little substructure in it that seems to be discrete in time. And with our eyes, we couldn't tell what it was, but our brains and our ears are much better at filtering these. So we listen to the data, and you'll hear so that is LIGO data. Oh, this is
This is not LIGO.
So that gives you a sense of some of the challenges that we're facing. We unplugged the phone, all is well. So one of the concrete challenges that I wanted to pose to this group is diagnosing our noise using slow correlations. So this is pushing down our sensitivity curve so that we give each one of our individual events a higher signal-to-noise ratio. So a really good figure of merit for thinking about this is called the in-spiral range. And what this does is it condenses all the information that you get with a full power spectrum density over all the frequency range into one number. So this in-spiral range for a binary neutron star source is the distance out to which we could see a binary neutron star for one particular detector that's averaged over all orientations and sky positions. So that's what this number means, and it does encompass sort of the most important aspects of our sensitivity in terms of the frequency content. So what we do is we can trend it over time, and you can see that there are, on the time scale of maybe tens of minutes, some pretty significant fluctuations over time, and these are the kinds of things that we want to diagnose. So this is an example from the first observing run, and something in particular that I wanted to draw your attention to. So this is the full course of the first observing run, so all almost 17 weeks. And these are the 2 detectors, and this is just each dot is a bin of time that takes the mean of the in-spiral range for that given point. And you do see some dips here. That just means that there was some loud transient, some glitch that pulled the sensitivity curve far up from what it nominally is. But what you can see is for the Livingston detector, starting at about week 12, so this was maybe November or so, we get this really significant 15 to 10 megaparsec drop in sensitivity, and then it goes back up, but then it drops back down again, and we lost about a little over 10 megaparsecs for the entire final month of our observing run. And eventually this was tracked down to a faulty temperature sensor. There was a temperature sensor that was emitting some electromagnetic radiation near an electronics rack at the end Y. So this means the end of the Y arm of the interferometer. But it took us months. This is so a month or more that we have significantly less sensitivity. So ideally what we want to do is we want to be able to find correlations between auxiliary channels that might help us track this down. So this is what we're currently trying now. We're trying to correlate our in-spiral range with different slow auxiliary channels. So these are things like temperature sensors, and even some of the faster channels too that measure more of the interferometer behavior. So we're using 2 different correlation methods for those time series. So one is Pearson's, which is just the covariance of the 2 variables divided by the standard deviation of each. And then also Spearman's, which is almost identical, except you're using the ranked version of these same variables. And the function doesn't need to be linear, it just needs to be monotonic. So this gives us results that look like this. So we can look at the in-spiral range, which is sort of this broadband kind of picture of how the interferometer noise is varying over time. And what we also do is this band-limited root mean square of our gravitational wave strain data. So this is about 114 to 122 hertz. So we can plot that time series and then some channel that has a high correlation coefficient using one of those 2 statistical metrics. So this is an example from the second observing run. This channel is at the end Y station, so the end of the Y arm. And it's a tilt monitor, so it's looking at the tilt of essentially the concrete slab that's holding all of our instrumentation. But on these kinds of timescales, it actually functions much more like a temperature sensor than it does a tilt sensor. So we're looking really effectively at variations in temperature. So once we've identified interesting channels, what we can do is we can plot the range, the band-limited root mean square of whatever range we're interested in. So that's also a good way of diagnosing, does this particular band of frequency, is that what's responsible for this variation in the range that we're seeing? And then on top of that, you can plot the channel of interest. So these are all scaled so that we can fit them on the same axis and compare them easily. Detrended, and then this range is also flipped so that when the noise goes up, so when your HFT band goes up, then the range also goes up instead of the opposite of what you would expect, or the opposite as you would expect. So some questions for this group. So sometimes this method works really well, but it tends to not work really well for a long period of time. So we'll find days or hours where we can find some really strong correlation with auxiliary channels, but it hardly ever lasts. And we think part of the reason for this is that these range fluctuations are, these are caused by multiple independent noise sources that are influencing the same frequency range. And this method currently isn't doing a very good job of picking those out. So any suggestions would be very welcome in terms of things that we could be doing better to detangle this problem. And a second question, so something that we're thinking that's along similar lines, eventually what we'd like to be able to do is to take our auxiliary channels and, depending on the behavior of the auxiliary channels, predict the effect that we're going to see on our gravitational wave strain channel. And this effect might be similarly on a slower time scale, or it might be transients or glitches that we're starting to see. So there are complications to this. So of course, right, the response might be very different in character. We need to ignore irrelevant trends, and the definition of irrelevant can be complicated. Some of our auxiliary channels are not clean, so the working group 3 is going to need to pay close attention to that. Some of them are glitchy, that doesn't reflect anything physical that's happening, it's just the sensor malfunctioning. Some of them just have some bad signal fidelity issues. Also, there's pretty much nothing predictable about what it is that we're looking for. So something else I wanted to mention, which is more of an advertisement than it is a problem, is that we have implemented successfully machine learning on LIGO data. So this is in the second observing run. It's a tool called GravitySpy. It's a citizen science project where we work with humans from around the world who will sort glitches. So this is some image, some time frequency spectrogram, into these about 18 different classes. And these are the classes that the detector characterization experts have defined as being most relevant to, most likely to be harmful to the search backgrounds. So the humans make this training set, and this is fed into a machine learning algorithm. And Ashish asked me if this was deep learning, and I said no, but then I looked, and it is actually true. Deep learning is already implemented as, I think, our neural net. So this is something that's, if you're interested in more details, you can check out this paper. Or also, if you're interested in helping us make our training set, then it's pretty fun. Go to gravityspy.org. Thanks.
I remember you mentioned about this auxiliary channel data, and as far as I remember, you mentioned that this has some multivariate time series aspect for multivariate time series, but I couldn't see. I just saw a single time series for auxiliary data. But is it in reality? Does it have some many time series for auxiliary?
Right, so if you count each one of even just the physical environment sensors, that's something like 200 or so distinct independent time series. Is that what you're asking?
Yeah, so do they behave almost the same? Like if there is signal, then all time series has some?
Sometimes. So temperature trends tend to be the same depending on, so if they're in the same building, then they'll tend to be the same, but that might be independent from another building. So sometimes they behave similarly, but other times not.
Thanks.
The same sensors will have the same sampling rate, but different sensors will have, so very low frequency sensors are sampled at 250 hertz maximum, but sensors that we value at much higher frequencies like microphones or accelerometers are sampled up to 16 kilohertz. Yes, so the question is, do we try to use the auxiliary channel data to remove the noise from H of T, our signal? So yes, there are linear regression efforts to do this. So we have some examples where this works really well. I was telling someone this, I don't remember who, but we have a periscope that transports the laser up into the vacuum chamber. And this has a mechanical resonance that's right in the middle of our sensitivity range, and this imprints itself on the beam, and we can subtract it very successfully using linear regression offline, which means after the data has been taken.